This is problem 5.61. And in this problem, we have a loop-to-loop roller coaster. It has a radius r, and on it is a car with a velocity v. This car is not going fast enough. It will fall off when this angle phi here well, it'll fall off at that angle if it's not going fast enough, okay? Now, the forces involved in here is the force of the track on the car, and then the force of gravity. And if it's not going fast enough, this force here will go to zero, and then gravity will take over, and then it'll just travel off in a parabola, okay? So, of course, you can see by the geometry here, this is phi also. And what I'm going to do is choose this as my x-axis, and this is my y-axis, so I can set up a free body diagram for this. Now, this car has a mass m, which is not important, but that car is located right there, okay? This car is actually, because of the force of the track, will have an acceleration, and that'll be a centripetal acceleration. It'll have an acceleration there. You can see that's along the negative x-axis. So if I redraw the coordinate system like this, then that mass will have a force on it due to gravity. Let me erase this up just a little bit. I'm afraid it's going to get off the video here if I'm not careful. So I'm going to raise this up a bit like this. This will be the x-axis. This will be the y-axis. And there will be a force of gravity, which makes an angle phi with the x-axis. And then there will be a force of the track. And then there will be an acceleration, a sub x, along the negative x direction. All right, that's my free body diagram. That's what I need to help me sum my forces. So given in this problem will be the fact that it has some velocity and the track has some radius. And what we're looking for is a relationship that relates the angle that this will fall off to the radius of the circle and the velocity that the car is traveling, okay? Now, my theory, first I'm going to need the sum of the forces on this mass in the x direction. And that's going to be equal to the mass times acceleration in the x direction. Okay, why don't I go ahead and put an m here just to note that, although it turns out we don't need that, there is a force on a mass. And also that the acceleration in the x direction, it's got to have a minus sign because it's pointing in the minus x direction, but it's basically equal to the centripetal force provided by the force of the track. Now, what I have to, let's see, we're going to do this under the condition that the force on the track is equal to 0. So what we need to do next is to just simply sum up the forces and see what we get, okay? So if I sum the forces in the x direction, I'm going to have a minus FTR. And then I'm going to have an x component of the force of gravity in the minus x direction. So that'll be minus FGX. And then that's got to equal the mass times acceleration in the x direction. Well, that's v squared over r times the mass. And then I need a minus sign here because it's pointing in the negative x direction. Now we're going to solve this under the condition that that force right there is 0. So we could see that F, the x component of the force of gravity, must be equal to the mass times the centripetal acceleration. I'm going to move up here. I'm running out of space down here. So you can see that FG, okay, well, why don't I just write FG as mg? mg, okay? And then I need its x component. Well, that'll be fg times the cosine of phi. And that equals then the mass times the velocity squared over r. I'll change that. I've been writing the v like that. Okay. The masses cancel. Bring g on the other side of the equation. And here's what we're looking for. Okay. The cosine, can't write today. The cosine of phi equals v squared over g times r. And that was actually, we were asked to prove that right there. Okay, so that's the solution to the problem.